This is lesson 3.4. We're going to be looking at perpendicular lines. We'll be looking at some theorems and proofs that go along with that. So we'll be looking at distance, the shortest distance from a point to a line. We'll be able to look at constructing perpendicular lines in class. We'll look at theorems, and then we can also apply this to many of our problems and real-life problems as well. So when we think about the distance, if we have a point, the shortest distance between a point and a line is going to be going straight there. So in this example, if I'm starting at this point A, I'm not going to go really far to the right and then curve around back to this line if I want to do shortest distance. No, I'm going to go straight that direction, in which when we do that, it will always create this perpendicular line. That shortest distance, see this AB here, is the shortest distance, and it forms a perpendicular set of lines. It's going to make those right angles. So this would mean that AB is a perpendicular segment to our line of K. So in this example 1, we want to find the distance from point A to line BD. So we can see in this picture, if we want to know the distance from line AB to BD, that would mean we're going to take the shortest distance, okay? We can infer this as shortest. We wouldn't want to know all these other, because I could take as long as I wanted to get from A to BD, but I want to know the quickest. What is the shortest route to that line? So looking in this picture, if I take this outer line, that's not going to be the shortest, right? We can see that if I were to bring this line in, it would end up being longer than my line. If I do the other side, same thing. This is going to be longer. So the shortest distance is going to be that perpendicular line that's there in the middle, going from A to C. So in order to find the distance from A to BD, we need to find the length of that segment, AC. Think about how we find length, how we find the length of a segment. When we're in a coordinate plane, we're going to use distance formula. So here we have distance formula. It's our square root of x2 minus x1 squared plus y2 minus y1 squared. So then we just plug in our coordinates. Remember, we need a label. So if I want to use A as my first one, I can do this one as x1, y1, and my C is x2, y2. Then all I'm going to do is I'm going to substitute these in. So I'm going to end up having D is equal to the square root of my x2, which is 1, minus my x1 of negative 3 squared, y2, which is negative 1, minus my y1 of 3 squared, and then I'm just going to solve. So I need to just simplify this. So negative times a negative makes a positive, so I have 1 plus 3 squared, negative 1 minus 3 squared, and I just keep solving. So 1 plus 3 gives me 4 squared, negative 1 minus 3 gives me 4 squared, 4 squared is 16, negative 4 squared is also 16, because that squared, remember, is going to make it positive, so I get the square root of 32. So my exact answer would be the square root of 32, and I could leave that. There's nothing wrong with it. If I wanted an approximation, I could know that it's about 5.7. Okay, that would be the rounded answer, but my exact answer, I can just leave it as the square root of 32. So we reviewed over what a perpendicular line is. Perpendicular is where we make those right angles. Now we have perpendicular bisector. Well, perpendicular we know. Bisector we've seen before as well. Remember, bisector is it cuts in half. So a perpendicular bisector is going to be a line that cuts another segment in half, and it's perpendicular to it. So it's going to be a perpendicular line that's going to cut that segment in half. So you can see in our picture here, our line N is our perpendicular bisector. Okay? N is cutting PQ in half, and N has a right angle. It is perpendicular to PQ. Remember, since a bisector cuts in half, that would mean its intersection point is going to be the midpoint. Here we have M is going to be the midpoint of PQ. It's the halfway portion. Then we also have some of these theorems that apply to perpendicular lines, several of them. A lot of times, remember, theorems can be things that we prove, or they're just things that we can agree on that they're true. So when we look at this theorem, we have linear pair perpendicular theorem. It just tells us if I have a linear pair that has two congruent angles, then those lines are going to be perpendicular. Think about if I have a linear pair where my angles are congruent. Okay, first off, linear pair is 180 degrees. There are two angles that are on that same line. The measure of a line is 180. So if those two angles are congruent, then that would mean that those two angles have to be 90 degrees each. So angle 1 would have to be 90, and angle 2 would have to be 90 degrees. If they're 90, then they're right angles. Then we have perpendicular transversal theorem. This theorem is talking about the line, that transversal that we've been talking about. Remember, a transversal is something that cuts two or more lines. It cuts across them. It doesn't cut them in half or anything. It just goes across two or more lines. Then, if we have a perpendicular transversal, if it's perpendicular to one of the two parallel lines, then it's going to be perpendicular to another one. Okay, and this follows part of the theorems we've been talking about with our corresponding angles. Okay, if we know they're perpendicular lines, then we know that corresponding angles are equal. So that would work the same with perpendicular transversals. If it's cutting across parallel lines, then those two angles, those corresponding angles, have to be equal. They're going to be congruent. They're both going to be 90 degrees, that right angle. Then we have lines perpendicular to a transversal theorem. If in a plane, if two lines are perpendicular to the same line, then these lines are parallel to each other. Basically, this is kind of opposite logic of the one we just did. If I have a transversal in which it is perpendicular to both, so here we already have the 90 and the 90, then I can apply it in reverse, saying that if I know these two angles are the same, now I know their corresponding angles as well. If those angles are congruent, then that means that M and N have to be parallel to each other. So in this example 2, we want to be able to look at our diagram and be able to prove the perpendicular transversal theorem. So first of all, think about what we know in this diagram. So we have these parallel symbols here. And I have a right angle as well. So those are going to be my givens. So if I start off with my statements and my reasons, I can start with knowing that H is parallel to K because it's given to me in my diagram. I can also say that angle 2 is a right angle. And it would be given as well. So using this information, first off, I can say that the measure of angle 2 is equal to 90 degrees based on a definition of a right angle. And let's take a second to think about what we're actually trying to prove. We're trying to prove the perpendicular transversal theorem. Perpendicular transversal theorem tells us that if a transversal is perpendicular to one line of a parallel set, then it's going to be perpendicular to the other one. So we need to prove that J is not only perpendicular to H, okay, here we already have that. We can look at this picture and know that J is perpendicular to H. But we want to prove that J is also perpendicular with K. So we're trying to work to where we can say J is perpendicular with K. Well, again, looking at this, since we know that H is parallel with K, most likely we're going to need to use that, then we can know if angle 2 is a right angle, angle 6 should also be. We know that 2 and 6 should be congruent because of our corresponding angles theorem. So angle 2 is congruent with angle 6 based on corresponding angles. So if measure angle 2 is 90 degrees, then that would mean we know, first off, if they're congruent, we know the measures are equal. So congruency means measures are equal. That's definition of congruence, or congruent angles. Now I can just substitute. So if measure angle 2 is 90, I'm going to plug that in. So I get the measure angle 6 is 90 degrees. All that is substitution. And so if measure angle 6 is 90 degrees, then that means that angle 6 is a right angle. I'm trying to write equals. I just need that angle 6 is a right angle. And that would be definition of right angles. And if angle 6 is a right angle, then we would know that J is perpendicular to K based on the definition of perpendicular. Okay. This is just one way you could do this proof. There's probably some different variations. Remember that proofs are just logic. You being able to show these logical statements, being able to make your case as to how J would be perpendicular to K in this case.